We often imagine time as a universal clock, ticking the same for everyone, everywhere. A minute on Earth, a minute on Mars, all in perfect sync. But what if this is just an illusion? Astronauts in orbit, clocks near black holes, do they all experience time the same way? Early in the 20th century, a revolutionary idea emerged. What if space and time are not separate but woven together, and time itself can stretch or compress? This concept would upend our understanding of the universe, revealing that time's passage depends on where you are and how fast you're moving. Join us as we explore how a simple question about light led to a revolution that shapes everything from our technology to our sense of reality. Before Einstein, Newton's universe was a static stage, space and time absolute and unchanging. But experiments showed something strange. The speed of light is always the same, no matter how fast you move. This defied common sense and hinted that our understanding of space and time was incomplete. Einstein's radical idea space and time are not separate, but form a single four-dimensional fabric, space-time. Every event has a unique place in this fabric, defined by 3 dimensions of space and 1 of time. The faster you move through space, the slower you move through time. This is why nothing with mass can reach the speed of light. Time would stop for it. Einstein's vision of space-time became the new foundation for understanding our universe. If space-time is a fabric, what is gravity? Newton saw it as a mysterious force, but Einstein saw something deeper. Gravity, he proposed, is the warping of space-time by mass and energy. Imagine space-time as a stretched trampoline. A heavy object creates a dip, and smaller objects roll toward it, not because of a force, but because of the curve. Planets orbit the Sun by following the straightest possible paths in this curved space-time. There's no invisible pull, just geometry at work. Even light follows these curves, bending as it passes massive objects. This idea replaced the old notion of gravity with a new, elegant picture. Gravity is the shape of the universe itself. Einstein's insight transformed our understanding of how everything moves. Picture an ant walking on an apple. To the ant, its world seems flat. But as it walks straight, it eventually circles back, unaware it's on a curved surface. We too move through a universe curved by mass and energy, following the straightest paths in space-time. Even light, though massless, bends around massive objects tracing these curves. This was confirmed in 1919 when starlight passing near the Sun was observed to bend, just as Einstein predicted. Gravity isn't a force pulling us, it's the geometry of the cosmos guiding our paths. The humble ant's journey reveals how our universe's shape determines how everything moves. We are all travelers on the curves of space-time. Gravity doesn't just bend space, it bends time. The stronger the gravity, the slower time passes. This is called gravitational time dilation. On Earth, clocks at sea level tick slightly slower than those on a mountain, though the difference is tiny. Astronauts on the International Space Station, farther from Earth's center, experience time a bit faster than we do. Over months, the difference is just fractions of a second, but it's real and measurable. Time's flow depends on your position in a gravitational field, a profound shift from our everyday intuition. We live not just on Earth, but within its influence on time itself. Einstein's theories reveal that motion also changes time. The faster you move, the slower your time passes compared to someone at rest. This is velocity time dilation. Imagine twins. One stays on Earth, the other travels near light speed. The traveler returns younger than the twin who stayed. This isn't science fiction. It's been proven with atomic clocks on jets and satellites. Even astronauts age a bit less than we do, as their high speed slows their clocks more than gravity speeds them up. Time is not absolute. It's shaped by both gravity and motion. Our journeys through space are also journeys through time. Relativity isn't just for black holes. It's essential to everyday life. GPS satellites orbit high above Earth, where gravity is weaker and their clocks run faster than ours. but they're also moving fast, which slows their clocks down. Engineers must account for both effects. Otherwise, GPS would be off by kilometers each day. The system works only because we understand how space-time bends and stretches. Einstein's theories keep your phone's map accurate, proof that relativity shapes our world. The fabric of space-time is woven into our daily routines. Nowhere is space-time strangeness clearer than near a black hole. As you approach, gravity grows so intense that time slows dramatically. To a distant observer, a clock near the event horizon appears to nearly stop. Signals stretch and fade away. For the traveler, time feels normal. They cross the horizon in moments, unaware of the boundary. But from afar, their journey seems to freeze at the edge, never quite falling in. Inside, all paths lead to the singularity, where physics as we know it breaks down. Black holes reveal the ultimate extremes of space-time. Here, time and space themselves unravel. Is time the same everywhere? Einstein's universe says no. Time is personal, shaped by gravity and motion, woven into the fabric of space. The difference in time between mountaintop and sea, the accuracy of GPS, the bending of starlight, all are signs of relativity at work. We are not just observers, our presence shapes the very stage of the cosmos. The atoms in our bodies, the space-time we inhabit, all are part of a grand, interconnected tapestry. When you look at the stars, you're peering through the depths of space-time, witnessing the universe's geometry in action. Our steady clocks are a local illusion. The true nature of time is a unique journey for each of us. In Einstein's universe, we are all travelers, shaping and shaped by the ever-changing fabric of reality.